most famous area, Italian area. Yeah. Oh, sorry.
Good morning. Buongiorno. If you know anyone who is still outside having coffee, please ask him or her to come in, because we are on our final leg. We were very exciting. We will have 4 very interesting talks in the morning before coffee. And then the last 2.5 hours or so, we will summarize and condense our work we have done in the past days. So you will all go back home with some condensed messages to your colleagues. Right, so let me start to introduce Gian Maria Sannino from INEA, and he will talk about the Mediterranean Sea circulation and high-resolution hindcast simulations and reanalysis.
Thank you. Good morning, everybody. So this is not the first one. Could you go back to the first one? Yeah, back. So, okay, this is the presentation, and I'm just going to show you how we can use reanalysis in our small domain, that is just the Mediterranean domain. And as you know, the Mediterranean domain is one of the 14 regions that belongs to CORDEX, this coordinated experiment that is just done to do downscaling of climate global projection. So we have a specific domain just for the Mediterranean Sea. This is the domain. And actually, the community behind this domain is very active. We have more than 23 different modeling groups. We have 12 atmospheric regional climate models, 10 ocean models, and 12 coupled regional climate simulations. So we are producing a lot of simulations covering the ICR5, and now we are going to also downscaling ICR6 simulation. There's also a database. This database is open to everybody. This is the website. This is very easy to access and download the data. And actually, since we are within the Copernicus framework today, let me say that now MedCordex is also going to provide this data, all the data, to the climate change data store in Copernicus. So there's a specific project, the name is Cordex for CDS, that is providing EuroCordex and MedCordex information to the ECMWF climate data store. But let's start and see what we have done in the past and what we are going to do within MedCordex. So we are doing, of course, evaluation, historical, and scenario simulations. And for the evaluation, we are just using, and we used it in the past, the ERA40 and the ERA interim climatological reanalysis data to force our coupled model. But this is very interesting because we are not using, now we can use also reanalysis specifically dedicated to the Mediterranean Sea. So we can use both ERA interim just to force our models, and also now we are at least 3 different reanalysis just to compare how our ocean component performs. So this is what I'm just going to show you. So among all the standalone ocean simulation that we have applied in the MedCordex exercise, we just look at these 2 simulations that are the highest resolution that we have. It is at both of them are 1/12 of degree resolution, are forced with ERA interim. They have 75 vertical levels. And we are just using to compare our standalone hindcast simulation with the reanalysis made available by Copernicus. These are the 2 reanalyses that we have now that are at 1/16 of degrees, so quite close to our resolution, 72 vertical levels. In one case, the only differences between these 2 reanalyses are just the different surface forcing. In one case, the 004, we have the ERA interim at 0.75 resolution, and in the other case, 009 reanalysis, we have the AMIP 1.1 fluxes. So it's a different kind. Here we have bulk formula. In the other two cases, for the INCAS, we use surface fluxes. So there are some differences, but they are close in terms at least of resolution. The other reanalysis that we are also comparing is the reanalysis made by Mercator. This reanalysis is more or less similar to the previous in terms of resolution. Here we have 1/12 of degree resolution and 75 levels. In this case, the horizontal resolution, the bathymetry and so on are very similar to the INCAS simulation. In this case, as in Copernicus, the model is the NEMO version. Here we are using a higher resolution ERA interim downscaling data. So the difference is mainly for the forcing. So this is just to give you an idea. So we are just comparing 3 reanalyses, one made available by Mercator, 2 by Copernicus, and then 2 INCAS. One did with NEMO, and the other one is with the MIT GCM. The 2 models, NEMO and the MIT GCM, share the same grid, the same forcing, the same bathymetry. So just looking at the surface circulation, this is just how to compare the 2 Copernicus and Mercator INCAS simulation with the IVSO data. So this is just to give you an idea on how the 2 models, the 2 reanalysis performs in terms of surface circulation. So they are quite similar, and except for the values of Copernicus, but I mean most of the let's say circulation that are the Alboran jar circulation and most of the small jars in the eastern domain are more or less well captured by these 2 reanalyses. On the contrary, the 2 INCAS seems to capture the main circulation, but not exactly all the jars. And this is just because, I mean, the reanalyses are assimilating SSH. So this is quite obvious that the 2 reanalyses are closer to the observations. Just having a look to the transport at the Strait of Gibraltar, because you know the Strait of Gibraltar is the only connection that we have between the Atlantic and the Mediterranean Sea. This is very important. And the way we reproduce the flux in the Strait of Gibraltar can have an effect of the simulation in the Mediterranean Sea. As you can see, all the simulation, NEMO, MIT GCM, that are the INCAS simulations, they have quite different values. And while the 2 reanalysis seems to be closer and also closer to the observation. But let me say something more about Gibraltar in a while, because this is a key point for the next simulation that maybe we have to perform. What about CSST? This is very nice. I mean, this is very strange, actually, because if we compare the Pathfinder, so the last SST coming from the satellite, that is just the blue curve, and you see that the 2 reanalyses are far from the observation, while the INCAS are closer to the observation. It seems that the SST is far from the observation, especially in the Eastern Basin for the 2 reanalyses. Maybe this is because actually the 2 reanalyses are not assimilating the SST, and this can be a problem. What about the rest of the Mediterranean Sea in terms of temperature and salinity content in different layers? This is how the 2 reanalysis, Copernicus and Mercator, are performing. So they are very similar in the upper layer, while in the upper intermediate, and deep layer, they start to be different. And actually there is a very strange behavior of the Copernicus data here, as you can see, between the 2. So this means that there's an effect of the surface, maybe for the surface forcing between the 2 Copernicus simulation. And this is where are the INCAS simulations. So it seems that while the NEMO model that is very close in terms of dynamical core to the Mercator reanalysis are very close, while the MIT seems, at least for the upper layer, a little bit colder. And this is related to the 2 higher fluxes that we had in the Strait of Gibraltar. What about the observation? This is just for Michel. this slide, because the pink curve is just a climatological data made by Michel in 2005, and we are still using your data, Michel, thanks. And as you can see, I mean, the Mercator reanalysis seems to be closer to the observation. What about salinity? In this case, the situation is even worse, because it seems that the Copernicus reanalysis are underestimating a lot, at least for the upper layer, the salinity, and there's also a very strange behavior here on the bottom layer. So there's a strong trends, positive trends on bottom. And what is very interesting to note is that the INCAS are closer to the Mercator ocean reanalysis that are closer to the observation. So it seems that the two Copernicus reanalyses are a little bit far from the observation, while the INCAS are closer as the Mercator ocean reanalysis to the observations. What about the Strait of Gibraltar? So you see that we can have different numbers because we don't have enough resolution in the Strait of Gibraltar. So it is just a matter of tuning the Strait of Gibraltar. But we know that the Strait of Gibraltar needs some care when we model the Strait of Gibraltar. This is just a few days of simulation. This is a forecasting for the Black Sea and the Mediterranean Sea that we are doing here, few kilometers north of here at the Enea. And you see that it seems everything is frozen. Nothing is moving too much because the ocean is low. But it's not slow everywhere, because if we look now at the Strait of Gibraltar for the same 4 days, we see that here the dynamics is much more, to say, strong. Because of the resolution, of course, we have something that is only 14 kilometers wide, because we have tides. So this means that we need a special care for this kind of points in our INCAS simulation and also for the reanalysis. This is how the tides works in the Mediterranean Sea. This is just a first example of a three-dimensional model that is able to reproduce the correct tide in the Mediterranean Sea and the Black Sea. So everything is just passing through the Strait of Gibraltar, but also through the Dardanelles and the Bosphorus. So we can do that, at least for the forecasting model. We are able to produce this kind of new model that take care of all this information. But if you now look to the, for example, to the what happens in the Strait of Gibraltar in the real world is not a matter of dynamics that is much more fast. It's also because you have a lot of physics, you have a lot of entrainment, you have mixing. So if you don't have the correct resolution, if you don't have the correct physics that is just triggered by tides, you are just missing something in your simulation. INCAS simulation, climate simulation, or even for the reanalysis. We know also that the Strait of Gibraltar is a place where you have hydraulic control. This is one of the few places all around the world where you can have hydraulic control. That means the bathymetry interacts with the tides, going this very nice hydraulic control. So if you don't have this kind of stuff, you are just missing something. This is what we have done. So you see here the generation and propagation of internal tides within the Strait of Gibraltar. So we can do that now. This is done with the MIT GCM in a non-hydrostatic version. And you see in the vertical the generation and propagation of internal bore within the Strait of Gibraltar. So we know that the models, the state-of-the-art models, are able to reproduce all this stuff. What happens if we just put all this stuff in a Mediterranean model? So if we put high resolution in tides, so this is what happens if we put everything in a model like this. This is an INCAS model. So we have tides, we have the correct resolution in the Strait of Gibraltar. These are just the two kind of tides that we have in the Mediterranean Sea. One is the internal component, the tidal, low tidal component, and the other one is just the component coming from the Atlantic side. Well, if we apply something like that, we start to have a different kind of mixing in the strait. So the gray curves are just the temperature. When we use tides, the black one is without tides. So there's a different kind of mixing. This is for temperature, this is for salinity, And the final result is that finally you have a different circulation within the Mediterranean Sea that affects all the main features of the Mediterranean Sea, like the deep convection in the Gulf of Lion. So if we apply tide or we don't have tides, we start to have two different kinds of Mediterranean Sea. So just to conclude, let me show you some news about Cordex. As you know now, Cordex has some flagship pilot studies. Among these 5 flagship pilot studies, there's just one that was proposed by the MedCordex community, actually by me and one colleague, on the role of air-sea coupling on small-scale processes on climate simulation, at least for the Mediterranean domain. And among the objectives for these flagship pilot studies, there is also this objective: determine the role of small-scale oceanic process on the evolution of regional climate, including regional aid budget. So in this case, we are also trying to understand if in a couple model there's a signal of tides and high resolution in the strait, and we can just monitor this signal in the future projection. So let me conclude just with this very simple statement. I mean, just let me summarize the first 5 points. The first 5 points means that that's good that we have reanalysis, but the reanalysis must be, at least for our point of view, that's just produce ANCA simulation, should be better than an ANCA simulation. Otherwise, for us, are completely unuseful because we cannot compare our ANCA simulation with this kind of simulation. It seems that, however, that the Mercator ANCAs, the Mercator reanalysis is a little bit better than the Copernicus reanalysis. So maybe this is just a message. Maybe it would be better to have all these reanalyses that are not too much within the Copernicus framework. And what else? The Strait of Gibraltar dynamics remain an issue for both reanalysis and ANCA simulation, but however, thanks to the MedCordex and the flagship projects that are just running now, we will try to address this kind of, let's say, issues. That is still an issue, but we really hope that in a couple of years will be not more an issue, at least in the ANCAs and the climate simulation. That's all. Thank you.
Thank you very much, Gianmaria. Very nice talk, very interesting. I'm allowing one question in the interest of time. Right, okay.
Thank you for this very nice talk. It's really interesting to have feedback from the use of these reanalyses. And I would very much like you to join the cost action on the evaluation of ocean reanalyses. If you're keen to participate to an intercomparison in the Med Sea.
I know,
because we really learn a lot doing this type of...
if I'm not wrong, Gabriel Jorda is already in the cost section, yeah. And if I'm not wrong, we are also trying to have a joint Baltex and MedCordex workshop that is also funded by the cost section, so your cost section, if I'm not wrong. So yes, it will be very nice to join the cost section for, I mean.
That's nice, and I wanted to make a comment on the differences in between the products. When we are doing data simulation, we choose one compromise or the other, and so we have differences. So some are better at the surface, others are better at depth. And regarding this bias for SST, it's also because we observe some biases in between observational products in that area. And we have to maintain a consistency with the forcings. So sometimes we make choices. But we have to discuss that with our users. Yeah. And better understand the differences and progress for, well, that's good for all the groups. And also, well, there was something else, but maybe we can talk later. Okay. Thank you.
Yeah, by the way, I agree with you that it depends on what is the final aim of the reanalysis. But in our case, we want to, how to say, assess the reliability of our ANCA simulation. In this context, I mean, at least the Copernicus simulation seems not to be a good way to do that.
Thank you for the discussion, Gian-Maria. Thank you for your nice talk. Can I ask Andrea Cipollone to come up front? Andrea is from GMTT, and he will so he will talk about the three-dimensional characterization of eddy activities in a global ocean eddy permitting reanalysis.
I'd like to thank first the chairman and the organizer for letting me present this work. And the idea behind this work is actually to see what was the impact of assimilation procedure at the level of a mesoscale. And typically we will look at the population in the global ocean eddy permitting reanalysis, and this is the reanalysis we will use is the CMCC1, so SIGLOR1. So usually, when you want to see the impact at mesoscale, people or in literature you see that there are studies about this looking at the signal, overall signal coming from the spectrum or variable like the eddy kinetic energy, and in this picture from Andrea. You can see the impact of the assimilation procedure on this kind of variable eddy kinetic energy. If you compare the red line, that is the eddy kinetic energy coming from free run, and the orange line, that is the one obtained by all the products assimilated, that in this case are sea level anomaly and in situ, you can see that you have a big enhancement in the eddy kinetic energy, and you can actually reach the observation line, that is the black line coming from the Oscar dataset. So this is a good way to see this, but you are not going much in detail. And if you want to do that, you need to rely on an eddy detection system. That is what we actually built for this purpose. So it's composed by two main parts. The first is a surface analysis that try to segment the eddies, the horizontal extension of the eddies coming from the extreme of the sea level, and then after subsequent cuts, subsequent contour towards zeros of sea level anomaly, you can see that the eddy easily emerge from at surface. But then this is actually let's say conventional analysis, but we then added a vertical algorithm that look for the eddy extension, and it's based on the profile of mean rotational velocity inside the eddies. This is not very used field, very used variable, but it's actually very important from a physical point of view, since it's related with the angular momentum of the eddies. And so it's quite stable along the trajectory of the eddies, and it's also stable through the layers. You see here that the signal still persists through the layers. It's able also to discriminate the eddies that are spurious ones, since are only surface eddies, and real deep one. So the main improvement brought by this system is that you can access now to the vertical distribution of the eddies. This is a 3D maps of the probability for an eddy to occur in a specific region. So the 80% means that you have the 80% of probability for an eddy to occur in that region. And you can also study which are the region where eddies mostly occur, and it's easy to highlight the zones of the areas where you have a higher mesoscale and high mesoscale variability, and you can clearly see also the impact of the 3D vertical of the 3D vertical analysis to see and sketch the difference in the vertical thickness. So we applied that kind of algorithm on 3 different data sets. Our reanalysis, SIGLO reanalysis, made by in CMCC, and then a twin experiment that's a control land that has the same physics and dynamical scheme of SIGLOs, but without 3D VAR, of course. And for independent benchmark, we use the Armor3D dataset. That is an observer-derived dataset that is able to generate a 3-dimensional ocean state, so temperature, salinity, and speed, starting from a statistical analysis on several observation products. And these are the first results. So now we are looking at the surface. The first row is the probability of occurrence for the eddies, and you clearly see the difference here. So in control run, you miss all the signal that are at mid-latitude, for example, and you only see patterns at ACC and western boundary currents. In SIGLOs, you are able to recover most of the missing variability, but and it's quite similar to the Armor3D result. This is we trust in this in Armor3D in this case, since we are looking at the surface, so it's well constrained by the satellite data. This is instead also at surface the high of the edge, the amplitude of the edge with respect to the surface, sea level surface, and you also can see the impact here. But the main differences comes when you goes to see the distribution at depth. This is the trajectory of eddies living more than 16 weeks versus their mean thickness. And you can clearly spot now the differences between the 3 data sets. In SIGLOs, all the trajectories actually pervade all the ocean basin, and the pattern of eddy mean thickness are similar with the pattern here in a control run. So this doesn't change so much the thickness of the eddies. But when you go to compare it with Armor3D, the picture changes a lot. So in Armor3D, you have very deep eddies, and this is actually related to the fact that, as the authors of Armor3D said, there is a strong correlation between the spatial variability at surface and at depth in the density field of Armor3D. And this is why you have this very deep eddies. So we now compare a measure of the eddy of kinetic energy, and we use relative eddy kinetic energy, and that is the fraction of eddy kinetic energy that is proportional that's generated by the eddies, and with respect to the total eddy kinetic energy. So you can see that for example, we don't have the signal at the tropics, since we cannot follow eddies that are with a spatial that are bigger than 1,000 kilometers of radius, let's say. So the first row is at surface, what we found at surface, and the second row is a vertically integrated result. And again, you see here the clear differences between a control run and SIGLOs. And at surface, SIGLOs are similar to Armor3D. But then when you integrate, when you on the vertical, you see again these big differences. And especially the armored 3D doesn't change so much in the Southern Ocean. So in order to validate this, the signals at depth, we compare the maxima of the relative eddy kinetic energy. Especially, more specifically, we compare the depth at which the relative eddy kinetic energy maxima occur, and we again compare it with the results coming from the observation from Argo float, and we use the maximum, the depth at which the maximum of eddy available potential energy occur. And they are not, of course, these are not, of course, the same variable, but you can, at least in the SEC, when the eddies are generated by baroclinic stabilities, you need to have the same correspondence, let's say. And you see, in fact, that the depth at which this maximum occurs is very similar, and it's at 7-8 meters. Again, we don't have any signal here in the tropics, but the general picture is in a good agreement. So this was my last slide, and so we compared the different data sets in order to see the impact of the assimilation on the mesoscale level, and we see that at the surface we are able to recover most of the variability, and for having a validation at depth, we compare it with the depth at which the maxima of the available potential energy occur. Thank you all.
Thank you very much, Andrea. It's very, very interesting. Any questions, Andrea, on eddy simulations? Magdalena.
Thank you, very interesting diagnostics. Do you know, I mean, when we assimilate altimeter, one of the key questions is how we project the sea surface on the vertical, and you mentioned Amor CD probably has too much of a projection. I mean, do you know what is the sensitivity to these assimilation parameters on the results that you are obtaining?
Well, in Armor 3D, what they do is that so the thickness is found in the speed in the current field. In Armor 3D, the currents at depth. The currents at depth are evaluated through adding baroclinic, so starting from the surface, from geostrophic currents, adding baroclinic contribution coming from the density field, from a gradient density field. So if you have a spatial variability, you will project it over the full water column. And they don't have advection, they don't have any other diffusion and any process.
Thank you very much for your response. We're coming now to the third speaker of this morning, which is Carlo Brandini. And Carlo will talk about the downscaling ICR5 reanalysis data for coastal climate applications, evaluation of uncertainty of coastal data sets.
Yes, thank you. Well, actually, I'm not Carlo Brandini, because I'm here on behalf of my colleague Carlo, who was not able to come here, and I'm going to talk about this downscaling procedure of ICR5 reanalysis data for coastal climate applications. Unfortunately, we don't have yet any results about the evaluation of uncertainty. And yes, the motivation of the work relies on the fact that shift in wind wave regimes are known to cause beach erosion and rotation. And in fact, many monitoring data and observed data suggest that an increase of the Sirocco wind almost in the northern Mediterranean Sea, and a relative decrease of the Mistral wind. So the primary goal of the work is to implement a cascade of numerical models, atmospheric and wave models, to assess the role of past atmospheric variability on the coastlines, and this will help the design of scenarios not only linked to the sea level rise, but also linked to the shift of wind wave regimes. So, more practically, the idea is to downscale the ERA5 data for the ERA5 time coverage, so the last 35 years, so to create a hindcast at very high resolution in the Mediterranean area. And by using taking full advantage of the improved resolutions, improved quality of the reanalysis data in terms of vertical and horizontal resolutions and data assimilation system and observation used. This will help the identification, as I said, of coastal wind regimes. This will allow an extreme analysis to compute the return period extremes of wave height, of course. And we are going to archive the full spectrum data and for more complete informations. And this will enable the implementation of new morphodynamic services. Here I show some example. And as I said, the final step is also to assess the uncertainty of this hindcast by using the ERA5 members. So this is the description of the numerical model chain that we already implemented in a very experiment as a first trial. So ERA5 will provide initial and boundary conditions every hour by using all the vertical levels. We are going to run a first WRF simulation, so atmospheric simulation at synoptic scale, 12 kilometers of resolutions, and with output every 30 minutes. Then a second nested WRF simulation on a smaller domain with 3 kilometers of resolutions and convection permitting and temporal output every 10 minutes. And finally, we are going to provide this atmospheric forcing to a wave model, the wave watch model, that has an unstructured grid able to reach 500 meters of resolution close to the coast. Okay, so talking about applications, coastal applications, in 2012 and 2013, me and my colleague were involved in the operational weather forecasting service in the framework of the Costa Concordia wreck removal project. And as you can see here, it is a very coastal application because the ship was very close to the coast. And every operations, as stated by the salvage master, were weather sensitive, of course. And during the night, the Halloween night in 2012, rough seas conditions led to a small displacement, of course, of a ship 300 meters long. So it was very important for them. And so we reforecast, better, we reanalysis this event by using the models shown. And I hope the colors, yes. Here is a zoom of the area of interest, and in red we show here. In red we have the ICR5 grid point, the nearest grid point. Then in blue the first intermediate WRF grid points, and in black the higher resolution WRF grid points. we compare this data with independent observations, an anemometer close to the red lighthouse here, and we have the black dots are observations. The red dots are the operational ECMWF analysis. Then the red curve is the ICR5, blue curve is the WRF 12 kilometers simulation, and the black curve is the higher resolution WRF simulations. And we have some statistical skill score that show marginal improvement anyway of the higher resolution WRF model here, for example, for the root mean square error. And even if we have a reduction of the correlation coefficient. And yes, similar results were found also by comparing observation of the wind gust. And we have a reduction in the bias. That is, the model is underestimating the observations. And okay. Then we run this numerical suite of atmospheric and wave models for a 1 month period in 2014. And we compare simulations with observation wave collected at 3 buoys in the Tyrrhenian and Ligurian Sea. Okay, this is the for the first buoy. This is the time series. We have a significant wave height on the y-axis and time on the x-axis. And in red model data, in black observations, we have some overestimation of the model, as it is shown also in this scatter plot. We have a root mean square error of about half a meter, and the bias of about 0.37. And this is the bias-corrected root mean square error. For what concerns the polar scatter plot, which is for the direction of the wave, I can show here the circular correlation coefficient, which is about 0.6. Okay, then for the second buoy, this is again the time series. We have again some overestimation for several days, but also some underestimation of the model. And in fact, the mean bias is reduced here because of the compensation errors, of course. And again, the root mean square error is about, and the bias corrected root mean square error is about 0.4. Yes, this is the circulation correlation coefficient, about 0.6 again. This is the comparison for the third buoy. Again, some compensation errors. Here we have an overestimation, but in this particular case, we have a pretty underestimation. That is, the model is completely missing an event of rough seas, considering that this is a coastal buoy. So a significant wave height of about 2.5 meters is pretty high, I would say. And the model is missing this event, as it is shown also in the scatter plot. This is the area of these points, basically. And yes, to summarize this very preliminary validation procedure, this is the summary of the statistical skill score, and we compare this data with what have been found in recent literature, in particular the paper by Mentaski et al. In 2015, that they evaluated a hindcast of about 32 years in the Mediterranean area, and yes, results looks pretty similar, even if they use a slightly different skill score. So we are going to homogenize this validation procedure to compare better. And yes, okay, I borrowed these slides from my colleague, so perhaps I'm not the right person to answer about the wave spectrum. On the left-hand side, we have an X-band marine radar data that has been used again in Giglio Island during the Costa Concordia removal project, that has been proven to provide reliable measure of sea state conditions, even if for a few kilometers of range. And it is possible so to obtain the wave spectrum by using this data. And this is a comparison for a particular date and time in January 2014. Left-hand side, we have the model data, and right-hand side, we have the X-band radar data. Okay, basically, we can two peaks are evident here. One from the east, which is perhaps I would say coming from, it is perhaps a swell wave because it has a higher wave period. And then another peak here from the southeast that has a reduced time period, so perhaps this is some locally wind wave. Okay, so to conclude, these are some very preliminary conclusions about this work that is aimed at assessing the role of past atmospheric variability on coastal conditions. The improved resolution of the ICR5 data allows the numerical regional hindcast at very high resolution close to the coast of the Mediterranean Sea. These are some of the results we have found for two test cases. One of very high an extreme event during the Halloween storm. Some improvements, of course, as expected, of the high-resolution atmospheric model. And for what concerns the significant wave height validation, we got, I would say, pretty good root mean square error, but the work is still ongoing. So that's all from me.
Thank you very much. And apologies for not identifying you correctly. You're Valerio Capecchi? Valerio. Thank you, Valerio. One question, two questions. Right. One, two.
Good morning, Hans Hersbach, ECMWF. So, do you only use the atmospheric forcing from ICR5, or do you also look at the ocean wave model we have? Because we have ocean wave also as a product in ICR5, because you're using your wave watch-free model for the higher resolution.
Yes, no. Well, actually, for the moment, we just use the atmospheric forcing coming from the ICR5. And then we use these two nested grids of the WRF mesoscale model to force the wave watch model.
How can you avoid using a nested grid for the wave model? I don't see why you don't have huge boundary effects from only having the wave model in the innermost grid.
Excuse me, can you repeat, please?
Yeah, how did you avoid having the wave model run over the whole domain? I don't see how you've avoided large boundary effects in the wave results by only having the wave model in the innermost grid. Waves propagate.
Yes. Yes. Again, perhaps I'm not the right person to answer to your question, because I'm dealing with the atmospheric models, basically, and it was my colleague that should answer better. Okay. If you are interested, later I can give you his emails. Okay.
But thank you, Valeria. You stimulated a lot of thoughts about your model. Thank you very much. Now we have the final speaker. I have the honor to announce Gian Paolo Balsamo from ECMWF. And he will talk about a roadmap to Earth surface kilometer scale simulations.
Thank you very much, Caroline. So it's a great pleasure and honor to be here at the International Conference on Reanalysis in its 5th edition. So I'd like to take the opportunity to thank the organizing committee that gave this opportunity to present. The outline of my talk covers 3 topics. So I'd like to show a few examples from land reanalysis research work, past and present at ECMWF. Some hint on the modeling enhancement we are working on, and then showing how much reanalysis are supporting already this research application. And then I would like to stress the importance of mapping challenges. So I acknowledge my co-author in this work. Please think of us as very enthusiastic users of reanalysis. That's really what we are. We are really tremendously excited about a new release like ICR5, or still we use very much ICR interim in our work. So, in particular, the work we do in our team is about coupling processes. So we try to reproduce and understand the physical and biogeophysical processes that occur at the interface between the Earth's surface and the atmosphere. And here you see a sketch of the basically the temperature profile that you have between the surface boundary layer and the land surface or the underlying surface. So this sketch is really putting the accent on the diurnal cycle. And the diurnal cycle is really one of the areas where we are trying to do better, to improve. This requires being able to represent things like snow cover or ice freezing condition, vegetation state and its growth and variability, and the vertical transport of heat and moisture throughout the soil media. And the same type of application is seamlessly moving across the different surface types. So it's true for biosphere, it's true for cryosphere, and it's true for hydrosphere. And as you see, the amplitude of the diurnal cycle varies very much, and also the depth of the boundary layer, the capacity of having different profile depend very much also on the resolution. So this is just to say that in terms of land reanalysis, there is a call for resolution, both in horizontal and vertical, and this is driven by processes. So you will not easily hear a land surface modeler saying, we are happy with this resolution. So as you know, land surface is very heterogeneous, and this guides really our needs for high resolution. At ECMWF, there is a range of models that is used for the surface-atmosphere interaction. You have heard about them in previous talk. I will not spend a lot of time. I just want to stress the importance of community development. All these models have been pushed by the academic community, and ECMWF has been benefit tremendously from the work done in this consortium. These are the models used for the oceans. I will concentrate on the model used for land, which is my area of expertise. So what you see here is a temporal sketch of the land surface model development that have entered after era interim. So we have used very much era interim as a driving meteorological forcing for studying this model development. So we have worked on a revised hydrology, a new snow scheme, a leaf area index, so a treatment of vegetation, introduction of carbon dioxide, natural exchange, and lately some modeling of the lake, so the inland water bodies. And we are currently working on a multi-layer scheme. So these are all research applications enabled by reanalysis. We focus on a few resolutions. So you saw there's a large amount of output from ECMWF. I focus here on these 4 different resolutions. So era interim that you know, era 5, which is the new kid on the block we are very excited about, CIS5, which is the new seasonal forecasting system that became operational this November, and then the ensemble and IRIS, which are the daily forecast output at 18 and 9 kilometers. And as Roberto mentioned in his talk, we are moving towards a coupled world. So we are trying to uniform and use the same model all across this forecast and reanalysis application. Talking about era interim land, so this is a land surface research application that has grown inside ECMWF and has been very much supporting the activity of reforecast. You see in this upper plot the soil moisture produced over a site in US in red in era interim. Era interim didn't have, for instance, some consideration for hydrology and soil texture. Era interim land in blue has managed to reproduce much better the soil moisture area. Here you have an example for snow depth over another site in Siberia. Era interim land against snow depth observation. And here an example of validation of energy fluxes and water fluxes. Right, why did I choose these 4 plots? Because you have some evaluation of the water flux, water reservoir, so the soil moisture and snow depth, and some of the energy fluxes. So once you have a greater match to observation in the water storage and the water fluxes, you can think of a better constraint of the water cycle at the surface. And this is really important because it's not easy to validate surface improvements. So having contemporary water fluxes and water reservoir in a better agreement with observation has been a way to qualify era interim land dataset. Now, this approach is currently used in the Earth to Observe project, and we extend it to multi-model. So basically using era interim forcing to have several land surface and hydrological models so that we are able to characterize a global hydrological data set from different models. And this has been recently published. Era 5 land is the project we're really excited about, and is led by Joaquin Munoz-Sabater. So he has a very nice poster, and I've heard all poster will be online, so I'd like to remind that all this work is also available, will be available online. So one advantage of ERA5 land is the high resolution. So while ERA land had a better land surface model, a more recent land surface model, in ERA5 land, we are trying to push towards a higher resolution. And we would like to match the 9 kilometers resolution, which is the highest forecast resolution we run at ECMWF. So the advantage is that we can study really coastal areas and inland areas that are relevant also for daily forecasting application. And you can imagine that looking, for instance, at a small island or a coastal feature or orographic feature, resolution will be really important for fields like soil moisture or snow, because you will have a better characterization of the surface. ERA5 and ERA5 land have a new component, which is the lake model. So if you happen to use the fields, download the fields from ERA5 and ERA5 land, you will have the opportunity to look at lake temperature, which is a new variable. Why lakes are important? If you compare a lake with a nearby forest, you have a very large differences in the sensible heat flux. So there are more than 200 watts per square meter in between a lake and a nearby forest. And the model is able to reproduce this kind of energy partition. But if that's provided we know where lakes are, so if we do have a map that reliably detects where lakes are. So this is all about the current modeling. I would like to show a few examples of our current challenges we are developed. In the near future, we are working towards enhancing vertical resolution. So you remember I said we would like to resolve the diurnal cycle better and better. And from the land surface point of view, the vertical resolution in the soil is one key element. We could prove that by comparing with ESA soil moisture data sets, so the ESA CCI. If we were to use a higher vertical resolution, we would improve the correlation with satellites' soil moisture product. And this for us is a big driver because it means that we get closer to the possibility to assimilate satellite soil moisture data. The model is in a better agreement with the satellite data. Similarly, the snow scheme, we would like to move from a single layer snow scheme to a 5-layer snow scheme. And we have already a preliminary result that shows that a multi-layer snow scheme would do better in terms of snow duration, which is one of the important things to be able to represent near temperature, near surface temperature, and weather parameters. So a new 5-layer snow scheme would improve by 5 to 15 days the snow duration at the surface. Again, this research is permitted by the ERA5 land configuration. So we use this configuration really for model development, and that's really how tremendously important our reanalysis to our research, internal research. And another impact of multi-layer snow scheme is the capacity to have a colder temperature in cold climate, which is one of the known limitations of NWP at the moment. Right, I gave it a hint that is not all about modeling, and it's being able to represent the Earth's surface is also a challenge for mapping. And we are starting now a mapping exercise at 1 kilometer. Why 1 kilometer? Because if we want to be able to reliably inform a model of 9 kilometers, we need to have a much higher resolution. And for instance, we are working on together with, in collaboration with JRC and ESA Globe Cover, to be able to detect lakes and water bodies at 1 kilometer resolution. So using an automatic classification algorithm. And a new 1 kilometer orography and bathymetry has been produced in order to support high-resolution modeling. Of course, lakes varies over time. So in his keynote, Adrian Simmons has shown how much the land cover variability is really changing in recent times. So, and this is a collaboration with JRC where we are trying to create a lake, a variable lake cover, which is much better reflects reality. So the lakes that we had 10 years ago are very different from the lakes we have now because of climate change and because of human activity. So lakes are built to support irrigation and agricultural activity. And finally, another very, very important challenge is urban mapping. And this is an area that we really feel we have to engage a wide community, because if you look at an intercomparison of urban data set, there is very large discrepancy. So we don't know where cities are in a automatic way or in a remote sensing way. And so this really requires a mapping effort for future high-resolution reanalysis. And we have started to work on that, but using only one example of mapping cover, which is the EcoClimap. So 1 kilometer is really a very ambitious goal, and ambition is almost part of the job description. So currently we run every day a 9-kilometer NWP model. So you don't see the land here, and this is what the model does. The model doesn't know where the land is. The land is given by the mapping and the physiography. And so being at ICR5, we are in very good company among ambitious colleagues. So they say this resolution, so 9 kilometer, is equivalent to 6.6 million points. So it's like a nice digital camera of nowadays. So we can plot this image on a UHD TV and see exactly every single pixel. You will see every single pixel with current technology if we want to display a 9-kilometer field. And NWP will not saturate the ambition for resolution. So this is the first example of a very, very high resolution. So 1.3 kilometer global using the IFS system. As you can see, so if I can go back one slide. Basically, so all those that wear glasses have these things in the morning when they put the glasses on. So, but basically, it's a much better resolved, much more process-oriented model. So the needs for resolution will not probably saturate anytime soon. So, and I would like to conclude on that, saying that land reanalysis do benefit from high resolution, both in the vertical and in the horizontal. We have some evidence. NWP systems are moving towards environmental prediction, and this is also a driver for resolution because emissions, for instance, are point scale. They are very, very high resolution. Supporting stream of reanalysis, a lot of our research is tremendously supported by reanalysis, and there is the climate stream, very, very long, several decades, hundreds of years. There is the satellite stream, and maybe there is space for a high-resolution stream that could support our challenges for the future. And there is great coordination in modeling activity thanks to the work of WMO and several committees. I think we could do better in the mapping activities, actually connecting the modeling and the mapping so that we would have maps that are readily available for modelers. And global kilometer scale reanalysis could be really an effective way to link better and more Copernicus sentinels, for instance, with reanalysis and all the wealth of geostationary and polar orbiting satellites which are already at kilometer scale. Thank you very much for your attention.
Thank you, Giancarlo. Thank you for these final thoughts, and thank you for firing our ambitions as well. So I could see that. We have one question.
Thank you very much. For your final 1 kilometer global land simulation, what would you do? What would you do for the atmospheric forcing? How would you prepare?
So for the atmospheric forcing, at the moment, to reach those resolutions, we do a downscaling procedure. So one of the two posters that I mentioned is about the downscaling techniques that has been used for ERA5 land. So at the moment, orographical downscaling.
So statistical downscaling is going to be?
Yes. This kind of simulation is really a 3D model, so it's a first of a kind, and it's thanks to my colleague Nils Vedi and the scalability team. So this is really a 3D simulation, so it's not something we can afford to run, but it's something that proves that is a stress test for the future, so to help, for instance, a vendor of high-performance computing to design new supercomputers that are able to run this resolution. So 9 kilometers is really a resolution that we can afford running at least the land surface right now, because that's the ERA5 land capacity.
There's one question. At the very back there was one.
I got a naive question. When you get a 1 kilometer's land information, how do you feed back to the 9 kilometers NWP?
At the moment, we already have the concept of subgrid in the 9 kilometers. So we use a concept called tiling. So underneath a grid box, we treat, for instance, separately forests, lakes, grassland, snow presence, and we have different energy budget calculated. And then what you aggregate is the fluxes, which is a much better thing to aggregate than surface properties. So,
thank you.
I have a very last one at the back.
At 1 km, I could imagine that land surface could change quite rapidly on the order of weeks, or I mean, if it's tidal based in days. Do you consider that at all? Or?
Yeah, I would think that 1 kilometer is really a challenge that I see for our entire community. So ECMWF is really, for this kind of resolution, is really relying on a community challenge. So what we can at the moment do at 1 kilometer is try to describe land surface. So the ocean part and coastal areas, we don't have yet that high resolution capacity. So this is really, that's why I focused on land surface, where we do have this kind of resolution capacity. So coastal areas, we don't have yet this. Yeah.
Thank you. I can see that your talk raised a lot of interest, so we will have a coffee break after Roberto had made some announcements.
Thank you very much.
Yes, thank you, Gianpaolo. So, Paul, can you come over? And Mitch, can you come over here? So before we break, I think we want to give some prizes to the people, to the Twitter people, and then we have thought to give a special prize to one special person. So the Twitter competition, we got number 1 is Mathieu Chevalier. Mathieu, with 137. Come over. Yeah. Thank you very much. Well done. And prize number 2 with 136 tweets is Joachim. Joachim, come over. Well done. Okay, now I want to... Okay, then we want to give a special prize to a very special person. I don't know whether you realize, but we had a very, very young scientist among us. And Paul spotted her when we were doing a poster session yesterday. So I would like to ask Deveshi back to come down. So, Deveshi, tell us, how old are you?
I'm 16 years old.
And where do you come from?
Folsom, California. It's near the capital, Sacramento.
And you had a poster?
Yes.
About what?
Atmospheric rivers. I did a case study on it and put it in a climatological context.
Okay, well, look. So this is a little present, just it shows, it's a small model of Fontana di Trevi. You need to go and see it and throw a coin, because they say if you throw a coin, you will come back to Roma. I'm sure you will come back to Roma with a degree in science, somewhere in science, because we were all very much impressed about you. And then there is a little present from the World Meteorological Organization to you, and this bring it back with a memory for this conference. And it's great to see people like you so enthusiastic. And you came, your parents, I think, paid for your trip. This is all great. Well done. Okay. Okay, so it's 10:15. I suggest we extend the coffee break by 10 minutes. So if you can all come back at 10:40. At 10:40 we start the panel discussion. Okay? Thank you.
Okay, please, everyone. Okay, so we're going to resume. This is the last bit of the conference, but it's not the least important. It is actually a very important bit. We've had this structure throughout the week of the 5 topics. I think it's fair to say that the 5 topics were well picked by the organizing committee because they cut through a lot of essential ideas. But we also had the panel discussion, which was cutting across. So we're going to have 5 plus 1 summary. We're going to have 1 summary by topic, and then we're going to have also a summary from the panel discussion. So I invite Shinya, please.
Morning, everyone. I am Shinya Kobayashi from JMA. I am co-chairing the section 1 of status and plans of reanalysis production. First of all, I'd like to thank the 2 ICR rapporteurs, Dr. Bo Dong and Dr. Jeffrey Olga, for great help in making the summary of this section. I'd also like to thank the Dr. Simona Massina and Dr. Michael Bosirovich in making this summary. So, I'd like to talk about the summary and key messages from this section. In this summary, firstly, I'd like to talk about the main points from each disciplinary reanalysis, and then talk about how reanalysis are moving forward, some open questions and recommendations. First, I'd like to talk about main points regarding operational centered development. This is what we used to call global atmospheric reanalysis, but it now encompasses other Earth system components. So we decided to put it in this way. Operational centers are continuing development toward improving quality and representation of the Earth system. There are some reanalyses that produce uncertainty estimate from ensemble analysis method, but we should keep in mind that those uncertainty estimates are the measure of the spread of ensemble rather than true uncertainties. Therefore, guidance on use and usefulness is needed. Discontinuities owing to observing system variations remain significant issues in the analysis, time series analysis. While reanalysis are used at climate timescales in many cases, coupled Earth system reanalysis may not extend back much beyond 2000 due to the limited availability of most critical observation for atmospheric constituent, for example. In this section, one thing we heard several times is that applied users are looking for as little latency as possible. That's the main point regarding operational centers development. Next, these are main points regarding ocean reanalysis development. Multiple global and regional reanalyses are available, for example, from Copernicus Marine Service. And they are moving toward eddy resolving scales, which is not yet possible with coupled reanalysis. Therefore, ocean-only reanalysis remain important. The next two bullet points are similar to atmospheric reanalysis. Longer time series and lattices are important in ocean reanalysis as well. There are some development in sea ice and biogeochemical reanalysis. And again, uncertainty estimates are explored in ocean reanalysis as well, using, for example, a multi-reanalysis ensemble approach. Challenges in ocean reanalysis are intrinsic limit in reconstructing unobserved variables and validation issue during sparse observation periods. Next, these are main points regarding land reanalysis development. Importance of land reanalysis is demonstrated in terms of carbon and water cycles and land management. Fully coupled atmosphere land reanalysis do not exist at the moment, but they would provide a major advance towards the better understanding of hydrology, snow cover, and so on. Next, these are main points regarding regional reanalysis development. Regional reanalysis project continues in various regions, generally supporting research and applied needs for higher resolution. In focusing on specific region, regional reanalysis project provide benefits such as going very high resolution, thereby providing a platform for new model physics development, enabling assimilation of additional observations, and estimating ensemble uncertainties. Now, this is a summary of how reanalysis are moving forward. The extension of reanalysis project and community continues, producing disciplinary reanalysis and also AMIPS, and progressing toward coupled reanalysis. Here, we use the word extension instead of proliferation, because proliferation seems to have negative context, and extension is related to a more organized and sought-out progression. New reanalyses are not developed for the sake of putting out new data set, but to emphasize some new development in method, data, and or quality. There is concern about exponential increase of data volume, and cloud storage is suggested as a way to address this issue. And these are the questions raised up in this section to which we don't have clear answers at the moment. Those questions are we ready for fully coupled Earth system reanalysis, or should we follow a prioritization approach? How to balance resolution, complexity, and uncertainty? How to deal with data biases, discontinuities, and inhomogeneity over a long period of time? Can accuracy and homogeneity be balanced in a single reanalysis for both monitoring and prediction? How to balance requirements for high-quality data over a decade or less, and data well-suited for studying multi-decadal variation in time, and how to support proper use of reanalysis. For the last one, there are some ongoing activity that address this question. For example, reanalysis.org and WCRP, a task team for intercomparison reanalysis. And the last slide is about recommendation. we came up with 3 draft recommendations. The first one is, given the extensive use of reanalysis at climate and weather timescales, and including climate services, as centers move toward coupled Earth system reanalysis, centers should embrace the notion of families or extensions of reanalysis to support climate studies using different observing system requirements. The second one is to improve communication with applied users. The last one is that improved or reduced latency of certain data products is important for applied user or operational climate services, for example. That's all for section 1 summary. Thank you.
Thank you. So, I'm sure there are lots of questions on these reactions. Do you all agree? Is it going to go on fine print and everybody agrees to that? Any suggestions, please? Questions?
Shinya is here. So, did you discuss frequency of update of this shorter period, high quality? So how frequent would you like to have a new release? Because it's the length of the reanalysis also determine the frequency in a way of how you can afford to reissue a new one.
I don't think we spent enough time to discuss about that issues, but I think it's important because if we update the reanalysis frequently, that means that the user community have to evaluate in the same pace. I think it's an important issue.
Yeah, I just wanted to make the comment. I think it is not really, so accuracy and homogeneity are not really competing goals. You specified that it's a question if both can be achieved at the same time. I believe they can be achieved at the same time.
Just on the first recommendation, which is a very nice one, but given the fact that most reanalyses currently, at least the global ones, are produced at NWP centers, there needs to be a case made for this sentence, centers should embrace, because you have to defend that in terms of their main mission. So Roberto gave a nice talk about ECMWF and how reanalysis is used, but it doesn't yet include use of extended 20th century reanalyses. And you could argue that it should, because the centers are extending the time scales, building coupled models and so on. But I think that argument should be in here because they need a clear motivation for doing this.
If I can just add to this one, it's true that the 20th century reanalysis, for example, was a benchmark for the ensemble method at ICMWF. So, but it's true that, yeah, there's still a lot of gap. Yeah.
Thank you. You mentioned the importance of providing guidance on how to use the ensemble spread as an evaluation of uncertainty, that it's not the true uncertainty. So the question is simply, how do you see, how should we proceed in this direction? How to make this happen, to allow users to use this ensemble spread in a better manner?
I think we don't have concrete idea to use those uncertainty information for the actual application, and it's something we need to work on that.
About intercomparison of reanalysis products, we've seen excellent examples like the Spark is very well, excellent. But I think it's not only important to focus on the intercomparison of the reanalysis products themselves, but also of the intercomparison of the data that they used as input, because at the end of the day, the end result is a reflection, partially a reflection both of the model that you use with model biases, different models biases, or characteristics, but also, of course, the observing system. So coordination between different reanalysis producers on exactly what data they use, how they use it, why they blacklist certain channels of certain satellite data, what are the experience, the difficulties. I think that would be very important. That would facilitate this is an important part of the knowledge we need to have in-house all the time when we start to do a new reanalysis. And we don't want to, to try, that has to be available, I think, easily, that knowledge.
Yeah, I agree with your point. I think that is something that is not currently readily available. But if we understand the difference between the different realities, I think we should go deeper into to understand what causes those differences. We should know more about difference in the model and input observation and so on. And I think that's something we should address in the intercomparison project. When we developed this project, one thing we should address is to create an infrastructure environment where that kind of comparison, for example, comparison of input observation can be done easily.
Okay, I think this question about observation leads us naturally to the report of section number 2. Thank you, Shinya. Thank you very much. And let's hear from Nick the summary from those talks.
Thank you. So this session was chaired by myself, Nick Rayner, and Stefan Bonneman, and Khalid Sharif and Michael Kozubek performed an excellent rapporteuring help, and together we discussed the outcomes of the session, and then I have also additionally reflected on the conference as a whole, because observations is a cross-cutting theme that has been brought up in many places through the conference, and so the summary statements that I'm going to present are a reflection on the totality of the discussions. So observations are the most important component of a reanalysis. What is assimilated and its quality is key to the success of that reanalysis. And this was nicely demonstrated by when Gil Campos showed the removal of the fog of ignorance when more observations are assimilated into a 20th century reanalysis. Work on observations for reanalysis requires a sustained, well-supported effort involving cooperation with reanalysis producers. So in my experience, this has worked very well in the ICR5 and ICR5 projects, and those are good examples of research projects which bring together observational development together with reanalysis production. Many reprocessed data sets for assimilation or evaluation of reanalyses have been presented here. We had a lot of excellent posters on these kinds of data sets and some oral presentations on these kinds of data sets, but this work needs to continue. Operational services by themselves are inadequate to support this research work alone. Operationally produced reanalyses are susceptible to changes in observing practice or in transmission practice of those observations, such as when the move to buffer was made. Adrian showed in his first presentation the consequence of that. Operationally sustained production of underlying key data sets consistent with the climate record is essential to avoid discontinuities that affect downstream services. Ongoing data research and recalibration, both of satellite and in situ data sources, are very important for improving the quality of reanalyses and for extending their quality back in time. In particular, data rescue is crucial for preserving data currently on either fragile tape or paper. We commend and encourage the continuation of the careful and painstaking work needed to do this and to pull them through into societal services. Reprocessing and making observational both actual climate variable and radiance series more consistent allows more of that information to be included in a reanalysis. If observational information is discontinuous, then sometimes the reanalysis cannot use that, so making it reprocessed and more homogeneous allows more of that information to be used and allows our reanalyses to then better reflect the observations. This requires a sustained program for reprocessing and making the series more consistent. The fundamental observational record is forever. Peter Thorne made this point in his presentation, and needs to be carefully preserved for reanalyses to come and for every other activity we may need it now, for now and in the future. This needs ongoing, adequate support, the careful preservation of the observational record. Because once observational holdings become fragmented, we saw from Peter and from Liz's presentation that it requires a great deal of effort to correctly reconstruct them. Future assimilation systems need to consider how best to use the observations and the information on their uncertainties. This effort, this research effort, needs to be supported. End-to-end propagation of uncertainties through observational processing is required, and then on through the reanalysis. The reanalysis community, as we discussed in the panel discussion, needs to clearly state their ongoing requirements for the observing system, considering also the known downstream needs of the applications. For example, a subset of the observations used are particularly key, it has transpired, and reduce uncertainty so much that they could be considered to be anchor series. We heard that as well in the discussion. And I've tried to pull out from the discussions examples where people drew out such key potential anchor series, and I've put discuss at the end of my list because it's just my list. So, sea surface temperature, sea ice concentration and thickness, Argo, GPSRO, radiosondes, surface pressure, scatterometer winds, and soil moisture. So I'd welcome your feedback on that list. The resolution of boundary or constraining sea surface temperature fields is key to reproducing precipitation over frontal zones and reducing tropical biases. Microwave SST should be continued and its resolution should be increased. Funding for new missions should be continued since that provides for future innovation. So we talked about the use of the GRACE information for water storage capacity. That's a sort of innovative use of those data, which I'm sure wasn't totally foreseen. So specifically, when we talked about preparation of observations for an analysis, I identified 5 kind of key activities that needed to be done in all cases. And here we've drawn out some specific and more detailed things that we noted from the session. So on data assembly, we need to conform to community standard formats to make that work easier. We need to be careful of the proliferation of observational databases. On data rescue, we need to recognize that observations are closely related to the people who made them and who keep them, and they are embedded in a landscape of politics. For the rescue of old satellite data, we need access to people's knowledge about what was done, and a lack of access to metadata, for example, on conversions applied, makes the process of homogenization much, much harder. On quality control, metadata, again, is key to make this effective. And when we think about making a consistent record and the need to apply bias corrections, we need to be careful that we use observations that can be used homogeneously together and not then introduce spurious trends into the reanalysis. And on then using the feedback from the reanalysis on the observations themselves, the use of that for breakpoint detection is a two-way learning process. Feedback information needs to be made more easily accessible, And it's currently not entirely intuitive what the variables mean, because you need a detailed knowledge of the assimilation system to use them. So I could have come up with 4 or 5 recommendations here, but I was limited to 2 or 3, so I've gone for 3. Number 1, research funding should be made available to support the ongoing rescue, reprocessing, recalibration, correction, quality control, and use of observations for reanalysis. Number 2, ICOADS, the International Comprehensive Ocean Atmosphere Dataset, is an essential foundation dataset for reanalysis. We had a couple of posters on ICOADS, and Liz mentioned ICOADS in her presentation in the session. But its funding has been cut to below a sustainable level. We can no longer maintain and improve the observations that are in that dataset. To keep the Marine Surface Archive alive, improving and contributing to future reanalyses, all reanalyses that we have discussed this week depend fundamentally on this dataset. There needs to be new investment in the core team. And number 3, the sea ice and meteorological observations for the Southern Ocean recently emerged from various archives of the late 19th and early 20th centuries should be digitized to improve our understanding and representation of this key region. So I'd welcome your feedback on those recommendations and whether there are others that we should also make. Thank you very much.
Thank you very much, Nick. Very good. So,
yeah, thanks, Nick. That's an excellent set of recommendations. I'd just like to pick up on one point with regard to the requirements for the ongoing observing system. You said the reanalysis community needs to clearly state their ongoing requirements for this system, but we're as close to the reanalysis community in this room as we possibly can be. So I'm wondering whether we couldn't just turn that into a very strong recommendation that there are key observations for climate monitoring, in particular through the use of reanalysis. Among these are that list. Because I do feel that a lot of, with various elements of the observing system, it always seems to be the numerical weather prediction argument that's used. It was a numerical weather prediction, well, we take the failure to proceed with the Cosmic 2B GPSRO radio system, GPS radio occultation missions that is perhaps one of the most recent ones. And there, the only reference in the official statement for killing it was, well, these data are useful for NWP, but there was absolutely no statement that they were also very useful for climate monitoring. And so I think if we could turn this into a strong recommendation, which could go to GCOS and work its way into the to the data providers, it would help.
Thank you. Thank you.
Hello. Could you? Yeah, can I talk? Could we go back to the last slide, please? Yes, about your recommendation too about ICOADS. I've been using ICOADS a lot myself, and you cannot emphasize how important that data set is. And this is one example where data rescue is happening all over the world, but at the end of the day, when this data is rescued, it ends up somewhere, and if it doesn't be, and it's not being collected again into one big archive, it will be lost again. So I cannot stress how important it is to have initiatives like ICOADS to combine all these data recovery activities into one archive, which everybody can use and which has been quality checked, has been homogenized in the sense of how the data is formatted. Yeah, I think this is the if you don't do this step, then there's a risk that a part of the recovered data will be lost again.
Yes, thank you.
Well, this is a follow-on to that. Yeah, I mean, when I look at number 2, that's all very well. I think there's an implicit assumption here, though, that Copernicus Climate Change Service
sub-project is going to do a perfect job for the land-based synoptic observations, because currently they're in a worse shape than ICOADS. I mean, ICOADS currently is a better collection. We can assimilate ICOADS data into ERA5, but we cannot assimilate a good representation of the surface synoptic data other than surface pressure prior to 1973. So I'm not quite sure why ICOADS it has been picked out here, unless you've got a lot of confidence that C3S can take care of the land but will not be contributing to the marine.
Yeah, one comment or sort of a question perspective, the list of key observations that you had, the first thing I was missing there is precipitation. And then that got me thinking that for our reanalysis, we have observations that we assimilate, but ideally we'd assimilate every observation there is, but then how do we validate? So should there be some sort of distinguishing between assimilated observations and validation observations? That observations that we can't assimilate are perhaps even more useful to tell us whether we did it right.
I think that's a really good point. Thank you.
Yeah, I think I see on your slide a lot of points about, you know, funding should be made available for this and that, and I think all of us here understand why, but I think maybe people outside of here may not understand why necessarily. So I think it would be very useful if this community could come together and make some clear cases. For example, based on Gil's talk, you know, he was showing, you know, the fog of ignorance. So what happens if you start to have observations, or if you don't have observation on our capability to use reanalysis to understand what was going on, you know, years back. So that's one case, you know. What happens if you start to lose observations, and what impact does that have on our capability to represent what happened in the past? Another case could be, what happens if you start to lose observations? What does that do for our ability to predict, you know, for the prediction problem that I think Roberto highlighted in his talk? So if the community come together and make some really kind of clear impact cases, that would strengthen the kind of should fund action that you're recommending.
Yes, thank you.
Yes, me?
Okay.
Yeah, you? Yes, I also have the 2 points that actually go back to the 2 interventions before. With the funding, when you say research funding, I actually would add research and operational funding, because these 2 things go very much together. And if we remember that research funding was, for example, putting the seed for an operational agency like EUMETSAT to build up a machinery that can actually do a lot of these things, but it needs continuous support from the research. But we should always think those 2 things together to really make progress, because if you would do a lot of research, that's probably not really sustainable in the future. You will always have gaps in that funding, so you need always the operational component to carry on. So I would add that. And the second point, that goes back to the validation question. I have seen a lot of comparisons here between reanalysis and some data. People were talking about satellite data, and then you compare 20 years of reanalysis to a data set that was produced with real time or so. So that's probably not the right data set that you would use to compare to the reanalysis. So I would ask for a little bit more care in how you select data to compare to reanalysis, and that is something that there are many activities. Is it the ESA CCI and others, and they are doing climate data records. So one should look what is kind of independent to the reanalysis in terms of observations used for those, and use those for comparison, and not just in a real-time precipitation product compared to a long-term reanalysis. You may see differences, but you cannot really judge why those differences are there. So that's. I don't know how to formulate a recommendation for that, but that's something I think we should probably bring in with the validation topic in general.
Thank you.
Okay, so I would just firstly second Adrian's point that the land data is in a far worse state than the marine data, and I think we don't know what we're missing. We don't know what value that might bring, but that's not to excuse that we need the marine. We clearly need ICOADS. But my main comment or query was, does this community have any view on future observing strategy, in particular the potential role of fiducial reference measurements that have full traceability to SI, whereby you change the paradigm where you have real confidence that the measurement, the true value of the measure lies within the interval. And I think that probably helps to address Jörg's point to some extent. Should we make a strong case that we need, not everywhere, but at a sufficient sample of points, full metrological traceability to SI or community standards and full measurement understanding so that we have a means to validate and calibrate future reanalyses?
Thank you.
Okay, thank you very much. Okay, I'll take the last one here and then we move to the next session.
Yeah, just very briefly. I mean, I have some difficulties in trying to, you know, understand how we can definitely say which is the most important component for a reanalysis system. I have some difficulties in trying to actually figure out how we can come to that conclusion.
So I would be a little bit careful. I was nervous of writing that down because clearly the entire observing system is important for a reanalysis. But this concept of anchor measurements came up, so I thought I would throw it out there and see what came back.
Okay, I think, Gil, we move on. We move to the next session on methods. Are you going to give a summary? Okay, very good. So you can make your point and then move on to the next topic.
Yeah, so while the slide comes up, which is actually a shameless ad for reanalyses.org, so you can phase out if you want, and if the Wi-Fi is working, log on to reanalyses.org and get your account now, please. And my point about what is the, if you want to give a single thing for reanalysis, it's SSTs. We have got to get the SSTs right. Every day, every week, every month, every year, as far back as we can go. It's the SSTs. It drives everything. So, end of that. I want to thank the previous two summaries. They did an excellent job. This is the C- summary, I'm afraid. I was charged to be the summarizer because I didn't chair any of the sessions, and it's not as good as the ones you just saw. But I do want to thank, it's not the fault of our rapporteurs who took excellent notes. It was tremendous. So what we've done here is tried to just capture what were sort of some of the themes that came out and the diversity of the, say, experiments with the assimilation interval or time window. So we discussed windows that went from an hour and yet was trying to get to decadal variations and said that was important, to windows that were multi-decades. So there was a lot of, quite a range of what was considered useful depending on the point, and item A and item F are actually in conflict. And I like conflict because you sometimes learn things. And I personally can't resolve those two yet. We had some discussion of experiments that were trying to understand the nature of coupling, and in particular, I thought Patrick did a really nice job of making the case against a strong headwind that the Serra system is strongly coupled. And that really surprised me personally. And Zhang's presentation that high time resolution was improving the coupled estimate of a very slow circulation. These were all methodological talks that point to things we have to consider for new ways to do things. There were several presentations in the posters and talks about the value of uncycled assimilation. Let's throw out the forward time step and just kind of use what we have, either from long model runs forced with SST or long climate model runs. So this was an area that I personally hadn't seen much before. There was some discussion, and in some of the other sessions as well, about the value of high resolution. And I think this is something that we need to continue to debate, because high resolution is expensive. So how much can you do? And there were lots of, most of the session really was about new observation types or new kinds of information being included in reanalysis. So going from handwritten documentary, it was cloudy today. How can we assimilate that from the 18th century, and isotopes? Trying to get to hundreds of years of variations, but even the sub-daily variations over hundreds of years. Paleo proxies to get to regional temperatures and tease out what's going on. Item D in particular for me was a real eye-opener. The idea that we're going to take one quantity and its rate of change to try to get to another quantity, the total snow. So it has to be an integrated long time window, but it was a different way. Item D and then E, another different way, using the total energy imbalance to constrain the ocean atmosphere. So these were, for me, new methods that I hadn't seen before. We had a nice talk about pushing the boundary of constraining the atmosphere all the way up to the thermosphere. I don't think we've ever talked about the thermosphere before at an international conference on reanalysis. It was like, and then there were, in the ocean talks, we were down the other direction all the way to near to the bottom. So we're really getting to the whole Earth system in our methods. Another constraint issue is how to include the model error in some physical way, and including the energy and budgets of the ocean as being important for the approach. Yeah. So related to Nick's talk, we spent a lot of time talking about what's not very sexy work. Understanding, characterizing, and including the uncertainties in the model error. But it's all of these highlighted how essential it is to combine the information in a sensible way. And there was a pair of presentations that as I reviewed them, I realized they had said basically the same thing using two different systems, one a hybrid 40E var and an ensemble of 40 vars, that when you try to take the uncertainty characterization back in time, if you just use it off the shelf, that is suboptimal. And it just doesn't work. And in one case, it actually made the model go unstable. And this was a very interesting, trying to use the reanalysis to elucidate climate model errors. I think this is an important application of reanalysis. We're going to try to project what's happening into the future. We need to know how to characterize the errors of those projecting models. And providing guidance to the users was also a theme of our session, and there were several aspects of the talks and posters that talked about that. So these are full sentence paragraphs that are starting to be ready to be dropped into a document somewhere. So I've got like 2 more minutes, another minute. So one statement that we want to, I believe, make is kind of brag, because it's not even close. Reanalyses are the most used data sets in all of the geosciences. It is so far and away. We need to toot our horn. So when we're talking about resources, forecasts are extremely important, but being able to do things across fields is also extremely important. And despite the fact that most used thing in all geosciences, reanalysis is not a research focus for most of the national and international programs. It's like we say a red-headed stepchild at times, and it's just kind of ridiculous that it's that way. I know there's a choir here practically that I'm preaching to, but so because most of the data assimilation development is taking place in the NWP centers, and they have a focus on real-time requirements rather than historical observation and use. So what we are recommending is that both the centers and our community at large incorporate some clearly articulated requirements for climate reanalysis. And we've had papers on some of this, but I think we have to keep kind of hammering away at why do we need this? What are these, again, Rita was saying, what are these use cases? And in this session, we saw several instances where the systems simply do not work off the shelf when you try to just take them back even 10 years, much less 100 years. So data assimilation specifically designed for reanalysis is a research gap. Now, I've had personally funding from NOAA to do this, so it does happen some, but it's not an ongoing sustained activity. It's coming in 3-year increments. So this is this common call. You can almost, I'm afraid after every meeting, you can say we need better observations, we need better models, we need better algorithms, bigger computers, and more money. But it is true that the topics on the methods specific to reanalysis are needed, and getting to this quantification of uncertainties is part of the reason that we want to do reanalysis. We want to know what happened in the past. We need to know what the distributions are, how they're changing. We need to be able to express that in a reliable way, quantified uncertainties. As one particular, rather large program, Copernicus is bringing substantial resources and activities to improving data access, understanding end-user requirements, providing operational services that are based on reanalysis. But there's nothing like a Copernicus for supporting the underlying research needed to improve and even sustain the services. So when we reflected on this a little bit, this appears to be kind of representative across many nations, and it's a concern. And that's all I had. Thank you.
Thanks, Gil. I was very happy to see that even when you had to do it on top of your head, you came up with 5 things. Okay, questions?
Thank you, Gil. It's about assimilation methodology specifically designed for reanalysis. Maybe I would say designed to take into account the reanalysis needs, because if we design something that takes into account the reanalysis needs, it will also improve the NWP. And we should not forget that reanalysis are essential part of the real-time forecasting activities of NWP Center. So, I mean, it's just change of wording, but also reflection. And reanalysis is not something for other users. It's essential for NWP in the extreme forecast index, the monthly forecast, the seasonal forecast. Depends on consistent reanalysis with the real time. So, just a comment.
Yeah, so there is a tension for me between reanalyses that are sufficient and adequate for helping with forecasting and reanalyses that are sufficient and adequate for getting long-term variations. And one of those bits of tension is that in real-time NWP, you don't get the future. You don't get to know the future observations. So if we're going to do reanalyses that have a 1-year time window, I'm not sure those, for instance, can make the case for having a strong relevance to NWP. So this is, I think we just need to call that out. It's part of, and like the ECHO reanalysis where you're doing a 24-year window, there I really can't see the NWP relevance. But if someone can make the argument the other way, it's fine too. I can see the relevance for validating climate models.
But Gianpaolo this morning laid out how he's using reanalysis to improve the model. And if you have a reanalysis that has a 1-year window, that'll still be useful to improve your model, right?
So we have to clearly articulate.
That model is used for near
it's not going to help
forecasting.
with the forecast.
But that model is used for real-time forecasting. I mean, it's not separate
but
things, right?
That's a two-step argument.
Well, what's wrong with 2 steps? I mean, it's part of the same effort and system.
We lose people at step 1.
Okay, admittedly.
Yeah. So saying it much more clearly than is expressed here, I think has a lot of value. And so let's keep working on those words for the BAMS article for sure.
Thanks, good summary. But I don't think my point is conflict with Patrick's idea.
Okay.
The only thing is we look at the issue from a different angle. I thought the decadal signals within the whole couple system, I treat it as this is it's an interaction. It's between the high frequency atmosphere and the low frequency oceans. They are, LC interaction results. Instead of look at the ocean as a force problem by the atmosphere. So this is, different angle. So the point, if in the whole couple system, we understand all the decadal signals, even the time mean futures, for example, AMAC, it comes from the whole couple system's signals interactions, then my point is, clear.
Okay.
But if we treat it, if the decadal signal is the force problem, then I think it's different. But overall speaking, personally, I don't think right now the data assimilation, anything we pursue conservation or perfectly balanced is the story of data assimilation. Because given the model bias, each step of data assimilation will break the conservation, will break the balance. That's the things we cannot avoid.
So I agree with you at the moment. I don't think we can avoid breaking the balance.
Right.
But I do think it's a methodological issue. Can we maintain the balance?
Yes, totally agree. So what we can do is we're looking for some good way to optimize, to minimize the breaking. But we have to break in something because the model is biased.
I had a comment on the category of reanalysis, the uncycled reanalysis, and it's maybe connect well with this just previous comment. One value I see is that uncycled or open loop reanalysis could really help to create a benchmark for data simulation reanalysis and to study a systematic model error back in time, because when we have little observation, we get hit harder by systematic model error. That's true both at the surface and in the stratosphere. So this could be a value. And the other topic is related to the conservation, in fact. So some of these uncycled reanalysis have embedded conservation, so they could be useful, actually. So it's, I'm pleased to see that they are part of the research. I still think that the statement, the most valuable asset are observation and reanalysis should be really very high. But this is a very nice research activity to create benchmark, and data simulation reanalysis should beat that benchmark.
The use of the word benchmark there is probably good for at least some of these.
Yeah, I was quite fascinated by these first attempts of doing paleoclimate reanalysis. And do you see the potential that these paleoclimate reanalysis get to a point where they really trigger something similar what happened with the surface data only reanalysis, namely that new data acquisition or efforts start to get more paleo data? It is so the observation operator for paleo data is of course challenging, but do you see that there will be some point where a lot more of efforts to get more paleo data?
So as I understand it, no one thinks they have enough money. I appreciate that, but from my perspective, the acquisition of paleo data is pretty well resourced. So they get to go out and scuba dive and get the corals, or go on expeditions and get the ice cores, and there's a tremendous community that's supporting that acquisition. It's a smaller community that's saying, let's do more than a statistical blending. And that's the newer aspect here, to me. But for me, the holy grail is to go seamlessly from several thousand years ago, where we'd have daily variations, to today.
Okay, if there are no more questions, I'll just thank you for your summary. And also the word tension that you used, I think is highly appropriate, because if you look back in those two papers from 1988, when people advocated reanalysis, they did it for two different reasons. The thing is that today at ICR5, we have heard about new methods this time, the smoothers. And maybe the smoothers versus the filters will probably be the way that we will explore those two dimensions. Okay, so I'll invite Adrian for the next one.
Okay, could I have the next summary? Okay, we had a group of 4 of the members of the Scientific Organizing Committee, Franco Desiato, Masatomo, Sonia, and myself. Franco has prepared these slides. He's a little bit modest because he's really the chair of the co-chairs, but he's really so modest that he asked me just at the last minute to actually give this presentation, I think because he felt I was the better stool pigeon if you start throwing awkward questions at this. At least I won't be back next time to be reminded of what happens. We were helped greatly by our 2 rapporteurs, Ilona and Ellen, and so we would like to thank them particularly. We had the largest number of posters, it says here approximately 90, and 13 oral presentations, so we're really not able to sort of go through and produce a decent summary of the posters as Gil picked out some of them. But what we will do, I think, for the written report here is trying to give you some summary of the nature and range of the posters. Also, in the written report, we'll have some overarching text on the importance of evaluation. There were some nice points made by Shinya Kobayashi in the panel discussion. He had a nice phrase about bringing into comparison, bringing producers and users together and building the community of developers to share experience. Some of that text that Shinya gave there, I think, would fit in very well in the written summary, although it's not reflected in these slides. So we had 13 oral presentations. I won't go through them with you now. They're listed here. Perhaps we will section them a little bit in the way that that Gil did. And as I say, I wasn't expecting to present this, so I think I won't try and discuss some of these because I'll end up talking about 1 or 2 and not the others. But we saw a range of, we've seen a range of types of evaluation, and we've seen a range of, seen the evaluation applied to the wide range of reanalysis project that's been discussed in the early ones. We had the important contribution from Gil, from a real user from the private sector. I appreciated that one in particular, personally anyway. So we boiled it down to 6 key messages and corresponding recommendations. By now we're the 4th group, so we're tending to repeat some of the conclusions of the earlier groups. Maybe we approached it through looking at the evaluations, but the conclusions come out the same, I think. The evaluation of the new state-of-the-art reanalysis data sets, the first strongly coupled data sets, 020C, and the newer what I might call comprehensive atmospheric reanalyses, MERA 2, ERA 5, have shown improved representation of several different processes, among them precipitation, soil moisture, and so on, but plenty of other things were shown as well. Developments towards increasingly coupled reanalyses really seem to us to be extremely promising from the point of view of what we've seen from the evaluations to date. Information from the ocean and land observations is regarded as complementary to that available from the atmospheric observations, and it's very nice to see the systems as a whole, working well. The third point concerns the collaboration with users from different sectors, and that's seen as crucial. As I say, I mentioned Gil's talk in particular, but there's others there. And although I think some of our other talks came from the public sector, I think some of the talks we saw last night on the, or this morning on the applications are also in effect contributing to evaluation as well. And so I think we've seen some very nice results there, and the importance of this collaboration with people trying to use the data the importance can't be overstated. We're very impressed with the, and Masatomo didn't have anything to do with writing this fourth bullet, we're very impressed with the recent intercomparison exercises. The ones that were foremost in the one that was foremost in some of our minds was the stratospheric reanalysis intercomparison, stratosphere, upper troposphere, carried out under the Spark initiative, but we were also reminded of the ocean reanalysis intercomparison. I mean, we probably saw some ocean reanalysis intercomparison, some very nice results at the fourth conference, and it's very nice to see that that's proceeded and matured. So those reanalysis projects we really see as exemplary. We're also pleased to see the beginning to focus on looking at extremes as well as mean changes, long-term mean changes, low-frequency variability, but also sort of monthly temperatures. But now we're beginning to see the extremes looked at. And we also had talks for the temperature extremes over land, the surface fluxes, which can be modified by soil moisture, and human management, the relevance of that was very nicely brought out by more than one presentation. And the regional reanalyses, we're very pleased to see those. We're learning new things from these reanalyses. There are additional opportunities for validation against data that perhaps are not assimilated in the global reanalyses. The regional reanalyses are carried out by people who know about the region and will look at the region more carefully than perhaps the global centres can. And we've seen some of the applications from regional reanalysis, even over some very well observed, like Europe. We see there that we can begin to sort of move downscale to start looking at river discharge variations in that, and so that's all very, very encouraging, I think, on the regional side. So those just map over into the corresponding recommendations. I'm sorry, Roberta, we have 6 of them because we had 6 bullet points, but we wrote less words than anyone else on them. So we underline the importance of continuous development within the reanalysis field, so we probably ought to slightly reword that to say we recommend the ongoing progress of development, which we've already seen anyway in some of the other recommendations. So I'm not quite sure when we produce the final report whether we'll keep the 5 sections or try and merge them, because there is a bit of duplication here. The second point, further developments of coupled reanalyses are strongly encouraged and viewed as of high relevance for the application to climate. So as with other section teams, we've come up with that conclusion. The need for specific, user-specific products and uncertainty estimates. I think someone said we wanted one number for the uncertainty, perhaps one number per variable per grid point, or something. But we do need to boil the output down from these reanalyses into things that really help users, or at least we need to provide the users with tools that make it easier for them to extract what they want from a reanalysis. WCRP is encouraged to continue its effect to promote reanalysis activities, and we have the task team for intercomparison of reanalyses, so we would really encourage that team to stick to its task, to look to continue some of the, or perhaps after a sort of pause for breath, to ask some of the other intercomparisons, some of the existing intercomparisons to be brought up to date when we have ICR5 complete, when we have JRA3Q and so on. But also to extend the intercomparison into other fields. I mean, there's a little bit of a question for WCRP, I think, because they have tended to have domain-specific comparisons, GWEX radiation intercomparison, studies of evaporation, and they include reanalysis intercomparison as a part of that. And I think we'll probably have to wait until your review is completed as to see quite how WCRP cuts its cake in the future. But we certainly would like, in some format or other, reanalysis intercomparison to be one of the focuses of your activity. The increased assimilation of land information, and there are some examples mentioned there in various talks, is really encouraged. Again, this relates to this question of extremes, because they really do improve the representation of extremes over land, and that's one of the key things that people are interested in learning about, and interested in understanding how those extremes change over time. And finally, more interaction between research groups resulting in regional and global reanalyses is encouraged. And somehow it's hoped that the international activities on intercomparison can somehow be extended to regional. I mean, the problem with you have a lot of different regional ones, that there will be some overlap, so there can be some intercomparison where there's overlap. But there ought, at least perhaps the people working on the intercomparison of the global reanalyses can recommend metrics, standardized ways of presenting the feedback that fits to observations, etc., that may enable different regional reanalyses to be intercompared somehow, even if the regions do differ from one to another. So with that, I'll thank you for your attention and throw this open to questions.
So I'd just urge an extension of number 4, and it's drawing a line also with GILS. Indeed, reanalyses are the most referenced and used geoscience resource. And that means there's going to be a real challenge to IPCC in the 6th assessment report. Now, I was the lead author on the 5th assessment report, and myself and Stefan Bronnemann, neither of whom would claim to be reanalysis experts, were probably the most expert in reanalysis. I think either one or both of the following need to happen. There needs to be a strong representation of the reanalysis community embedded in the lead author teams for the chapters, particularly as Working Group 1 is going thematic now, which means that reanalysis will be considered across all of them. And second, I would urge that task team to produce a paper that provides a strong peer-reviewed basis as to what reanalyses can and cannot be used for, which reanalyses should be used for what purpose, because otherwise I think we're going to give the 6th assessment report a major, major headache.
Yeah, those are good points. I'm not going to argue with either of them. I think the slight problem I have is that we certainly can, through evaluation, point out that this reanalysis is good for this, that reanalysis is good for that. But it may look to the outside world that we're just cherry picking. We're picking the reanalysis that gives us the result we want to prove our point. So I think if we are going to encourage intelligent use by the IPCC authors of reanalysis projects, the evaluation that's carried out of on the recommended reanalyses is of the utmost importance because it's the comparison of the fit to observations, it's the agreement with one or two other products, etc., that enables us to say, yes, we think you can rely on this reanalysis for this purpose because for this particular variable, the model isn't believed to have serious, simulating model isn't believed to have serious biases. The observations are relatively homogeneous over time and they're fitted to within a similar accuracy over the last 3 decades or something. I mean, we need to back up statements that this is the best reanalysis for this purpose with hard evidence like that. Otherwise, we will just have accusations thrown at us, I believe.
I have a comment to today's activities on intercomparison of reanalysis. I have a comment on the intercomparison of reanalysis. So we talk a lot about coupled reanalysis, but I will say that we should also talk about coupling of intercomparisons. For instance, because when we look at ocean reanalysis rely a lot on the atmospheric forcing that is prescribed. And I would say, for instance, for the sea ice intercomparison, 1/3 of the work was doing an intercomparison of the atmospheric reanalysis in the polar regions. So maybe this is also something that should.
That's a good point. Yes. Someone else taking notes of this. Franco, could you try and remember that point? Because we need to, or Ilona or Ellen, please.
Okay, yeah. I was afraid Matthew was going to take away my thunder a little bit. But I wanted to give a word of caution on coupled analysis as well. It's still strongly encourage it, of course, but we have to do intercomparisons of coupled analysis, as Matthew says, in the context of on the intercomparison of ocean and atmosphere, and for that matter, land surface analysis is on their own. I mean, the work of Karina, I think, shows that, I mean, if you look at something like the ocean in a very detailed context, there's information to be had, and we don't want to throw that in with the kitchen sink and say it's all solved now. So it's very important, I think, that we continue to do this in a comparison on all fronts.
I don't think we'd argue there. I think Patrick in his, was it Patrick or Dinon in one of their talks did refer to the, when it's good, it's very, very good, but if some element of either the atmosphere or the ocean has a serious problem, the problem can be propagated from one domain to another. So certainly the evaluation is critical in that, and also the multi-domain evaluation.
Okay, I do not see any further questions. Gil, one question. Okay. You are the one who asked for one number for the uncertainties. Okay. There you are.
Thank you. I don't know if my questions or my comments are for this session or for the next one, that are application, I think, or not. Anyway, from the user's perspective in the industry, I can say that I would say that the 3 top questions we got from the users is which is the best reanalysis? And when you say use all, they don't like this answer. They want to choose one, to have someone that tell you which is the best one. The second question is why different reanalyses they show different results. And so that makes me think, makes all the analysis you want, all the reanalysis you want, but they converge to the same results. And third, the most important question is the consistency of the reanalysis. And this is probably the thing we need to work more, how to be sure that the reanalysis are consistent over time. Yeah. Because in our field, a slight difference can bring very different results, and that is one of the main issues. And finally, about the uncertainty, as I said yesterday, it's something that we don't want to look at, the uncertainty, because we don't know how to handle this. But if the uncertainty that you provide is very big, you kill the product. So maybe it's better to wait some time until you show us that the uncertainty is not that big. Obviously, I am joking a little bit, but I think it's important that not to be sure that the uncertainty is something that we can accept.
Yes, I mean, there is this point that the requirements of different, that came out very nicely in the user survey, that the requirements of different user sectors are different. I mean, some require high resolution, some require homogeneity and don't care much about the resolution. And some people are already complaining that they can't deal with all this data that ICR5 is throwing at them. They want daily averages, they want this, that, and the other. So, and with uncertainty, I mean, the uncertainty that we calculate with ensemble systems is very much a local uncertainty, the uncertainty of the analysis at a particular time. It doesn't say a lot about the uncertainty of the reanalysis when used to calculate the average temperature trend over the last 30 or 40 years, because that's going to depend on things that are just not sampled by the ensemble approaches we use, or only partly sampled through the SST variations. So, I mean, I think although we're trying to provide uncertainty information, it has to be taken with a pinch of salt at present, and the intercomparison, the evaluation of one reanalysis against another, against independent observations, is still probably going to be the primary source of uncertainty for many people, rather than the products that are produced on the fly.
Yeah, this is, I think, it's a need. I don't know in which section this recommendation needs to be. It's regarding the evaluation of the observing system and observation impact, whether we are well prepared. Yeah. We have new observations, so the methods are not always adequate. And this is it takes a long time to do. And at the moment it's not properly resourced. But I think it's a duty that the reanalysis community has to evaluate the observing system.
Yeah, there's a certain amount of that is done by the producer on the fly. I mean, I think I don't know if it came out. We had a poster on monitoring, which I didn't get round to, for monitoring that's done for ICR5. But certainly just by looking at how the reanalyses progress over time, when the observing system changes, how the product changes. I think there's a lot of at least qualitative knowledge about the role of different parts of the observing system, but that information, a lot of that stays in people's heads, unfortunately. It doesn't get down even onto paper, and that's because it's sometimes difficult to be scientifically rigorous, I think, in publishing it. But I think that's an area where we perhaps need to put a bit more effort. I mean, it can be done by doing, a JRA55C for the satellite data. It can be done at the large scale, but there's a lot of granularity in the observing system, so the impact of this scatterometer, that scatterometer, etc., the shift from this one to that one, all that sort of stuff is difficult to encapsulate, but I think we could do better.
Okay. Thank you very much, Adrian. So we'll move on to the last summary before we have the panel discussion summary.
All right, I'm summarizing the application session. This was put together with the session chairs, Caroline Richter from WMO, Mitch Rixon from WCRP, Jean-Noël Thibault gave input
also this morning via email. We had 2 rapporteurs helping us a lot, Semyon Szymanka from the Swedish Meteorological Hydrological Institute and Michael Bechtold from the Catholic University of Leuven. Right, you won't be very much surprised. We didn't come to conclusions which were completely different from what you heard before, but maybe we have a bit different angle just looking at the issues from the application side. So there is a growing number of applications. We didn't bother to put them all down because it gets tedious, but it's growing very much and the applications are very wide. The sophistication of use is very different. So if we want to serve everybody, we might not serve everybody with the same answer. So we probably have to provide for a variety of users. Right, so there are some common wishes, like easy access, or users want to bring their laptop to the cloud, they want timeliness, so that they can quickly do their applications, and they want guidance. That seems to be common to the users. There is a desire for higher resolution and accuracy for surface variables, which is driving the demand for regional reanalysis or various downscaling techniques. Just to remind, what we actually wish for is the true state of the weather and climate and how that changed over time. And what we get from the reanalysis is we draw information from some observations and models by some data assimilation technique where uncertainties or whatever measures you do to describe your accuracy, they're not clear. And there was a discussion what needs to improve and what's the most important bit. Yeah, we need maybe more than just some observations and models, or maybe also some more from the data assimilation techniques, just to get closer to our true estimate of weather and climate over time. Maybe. Right. So where are the gaps? This is also thrown in as a stimuli of a discussion. Right. One of the Achilles heels, we can discuss whether it's the Achilles heel, is observations missing in data sparse regions, or observations missing in historic periods where you had little data, or observations missing for less constrained parameters. So we agreed on that sea surface temperature is to be paid attention on, at least also the sea ice, the deep ocean and the soil moisture. But probably you want to skip in and lengthen the list. The sources of uncertainty come from lack of observations, yeah, but they also come from model errors or lack in data assimilation technique. So there's plenty of work to address this. One thing pointed out during this conference is that the anthropogenic influence is not yet considered with respect to irrigation, land use change, maybe also the urban developments. There is a drive for the usage of more and higher resolution Earth system observations. So, of course, we want not only to observe the atmosphere, but the whole Earth system, and then we don't just need the coupled modeling, we also need the observations for this. The aim is to get the balances right, and this is important also for long-term changes. So you might have users who are just interested in the long-term changes and they do not think about the balances, and you can't always expect from the users to clearly state what kind of research is needed to better serve them with the data. There are areas of special interest, like the coastal area, which is, of course, especially difficult. Area of special interest, also the urban areas, which might need a bit more of development. And one question which came up is, are we getting all the information out of the system which we could have? So that's also something to think about. whether it's a methodical improvement which could help us. Right. So we tried to group what is needed in future. Firstly, what do we expect from the observing system, which serves as an input? Of course, we need the preservation and extension of an observing system, and you would say it's a no-brainer, but maybe it has to be stated again and again so that funding is secured. So that's both for the critical in situ data and also for satellite measurements. We need the data rescue of historical data, and we need a continuous observation reprocessing. Maybe that's a point that Jörg Schulz did in the discussion earlier. Right, from the producers, we need, of course, to make sure there is a continuous production and not some rupture. If you have plenty of applications, users who build on this service, it should be clear that it's continued. From producers is always asked to do it higher, faster, longer, better. So I always want higher resolution, always fast access, always longer time series, better quality. You can again say it's a no-brainer, but still that will improve applications, that will improve the value of reanalysis. So although it's a no-brainer, I just want to state it. It's something what is needed. It was discussed that the coupling of the components of the Earth system is a new hot topic which will allow us to get higher and longer and better quality. So coupling with the ocean, of course, land, ice, atmospheric chemistry, but maybe in future also a biosphere. We think it's also something new from the community. So uncertainty characterization, maybe something the community can contribute to, keeping in mind that they should use the independent data fit for this, which was said earlier by Adrian, I think. We also singled out intercomparison and evaluation activities for both global and regional reanalysis as a good tool to get the community together. And an enhanced communication is always valid, is always good. So, for instance, this conference, I think, was very much appreciated. I heard from many users, so my personal thanks especially to Roberto and Paul for this beautiful conference. So, thank you.
So questions for section 5?
Did you discuss about, by the way of enhanced communication among users themselves? Because there may be many users of the same products with similar applications that they may want to exchange views if they had the platform?
Okay. So I think we have to distinguish here whether it's users in science who freely exchange ideas, or there might be users in industry which are not so keen on sharing their ideas. And I'd like to comment, for instance, on we need one number for uncertainty, we need one reanalysis only. I know that there are wind energy users who use with benefit different reanalysis. And I don't know what they're doing about uncertainty because they won't tell me, because there's money involved. So they won't always tell you their recipe. So just to keep in mind, there might be user requirements people are a bit reluctant to tell in the room. Maybe they tell you during coffee or so. I think this kind of conference is very good to exchange, but not all users might have funding to come to this kind of conference. So I think it's more the intercomparison which would have the possibility to bring together the community.
I want to follow up on your point that industrial users can be a little tight-lipped, but at least some of them are excellent at uncertainty characterization. So in 20th century reanalysis, we give out 56 members. And we have a lot of users that want all 56, the whole 3D field, and then they'll do what they want to provide their downstream application, including wind probabilities.
Thank you.
You mentioned perhaps the tendency of some users to keep their methods, etc., to themselves, which is understandable. also partly understandable, but a problem nevertheless, is that some of the observations you need are being taken by countries but not shared. I think probably soil moisture is one of them. So there could equally be a recommendation to producers to do the best they can to follow WMO resolutions, which have tried to encourage them to exchange more climate data. Unfortunately, the climate resolution doesn't have quite the teeth that the resolution 40 does for weather prediction, but we've certainly there is some scope for getting some of the observations moving, and I think it helps to actually point out that perhaps it helps anyway to point out that there is this quite a big user requirement for timeliness of data. There tends to be a statement in some cases that some countries that we can't make these data available in nearer time, but we could after 2 or 3 years for climate purposes. But I think climate has become a bit more pressing than sometimes these people would suggest.
Yeah. I agree. We should make the statement that for the very beneficial reanalysis, we really need the data input from the different nations all around the globe and also the old data. I think that's something people can understand. That would help.
As a user of reanalysis, I find the thing I care about mostly is time resolution. So mostly when people say higher resolution, they seem to be talking about higher spatial resolution. So ERA5 is, in my eyes, a big improvement on ERA interim, not because it's got a higher spatial resolution, but because it's producing hourly data, which means I can consider its output fields as a continuous process. And I worry a little bit about the regional reanalyses also producing hourly data. If you're at a 5-kilometer grid, we need the data output much more frequently than that.
Okay, noted.
Okay, last point here.
I mean, just talking during these days, it has been for me very illuminating on the amount of users and the kind of users. So there could be from very sophisticated users to users from very small companies that I think we also need to cater for. They cannot come here, they cannot download a lot of data, they need very simple information. And it could be, I think it could be very nice to provide, I mean, that's for Copernicus or others, some sort of platforms, interactive platforms for users, small users, to exchange information and make the most of reanalysis.
Okay, very good. I think we can move on. So now we have asked Michel to provide a couple of slides as a summary of the panel discussion that we had, which I think it can be useful to have also a summary to insert in our report. And then we will have 5 minutes for, again, overall discussion. Someone has a couple of other points to bring up. And we are aiming to close by 12:30. So Mitch, floor to you.
Yeah, if you can pull up the slides. So I have only 2 slides which are meant to summarize the panel discussions. The panel discussion was organized along the reanalysis value chain, so you won't see really big surprises. And a lot of these items have actually already been discussed throughout the week and also during these summary discussions. So regarding observations, Jörg pointed out the importance of data rescue and data stewardship, the importance of fundamental climate data records, and the point was also made this morning that these data can also be used, I mean, climate data records can be used also to verify the reanalysis. Uncertainty quantification, that feeds directly into the data assimilation stream of reanalysis, so this is also fundamental to characterize that. We have also formal ways to justify new missions or continuation of former missions. These mechanisms should be used as a way to forward user requirements from this community too as well. Some people flagged also the fact that there was still room to exploit a larger number of observations. Roberto said currently the data assimilation, reanalysis systems are ingesting 7% of the available data. We can surely explore that more, especially when it comes to regional reanalysis. In terms of Earth system reanalysis, Stephen pointed out that we have a range of possible ways to couple the different components. But we're usually driven and constrained by the available resources, whether that's CPU cost, or infrastructure limitations, or information content of observations. Another restriction is that usually we don't even know exactly how to transfer those quantities or properties across domains because we don't understand the processes. But bottom line is that the resources are really currently a critical bottleneck there. Anarita, she also made the point that reanalysis is also a fundamental tool for model development and weather and climate predictions. She pointed out the example of the S2S project, so sub-seasonal to seasonal timescales, but that's also valid for the other timescales, of course. Another point that was made there was the need for balanced initial conditions, and in reanalysis that may be a different requirement from with regard to the climate monitoring on the other hand. In terms of evaluation and intercomparison, we had numerous plea to coordinate the community around those efforts, and also have the community organized around common infrastructure to support the work of the community. So this also came strongly throughout the week, I think, and TIRA is one example of that. The reanalysis.org was another one. So we need further work to that. And as was pointed out, currently, for example, SRIP or IP have been a domain-specific reanalysis intercomparison project. Now, as we move to coupled reanalysis, there will be a need to have a more comprehensive approach to those intercomparisons efforts. And finally, on application, we realize really that there's a growing number of users in the research community, of course, but it's really also, we're seeing a growing use of reanalysis on the service side and on the policymaking side. As a matter of fact, now Jean-Luc Tepeau, who had to leave the conference midweek, is in Bonn currently. And in Bonn, there were several statements, formal statements, made on the state of the climate using also reanalysis. So this is really a good sign that the community is now gaining trust in those products, which were barely known even 5 years ago in those communities. Another point was that the ground segments, infrastructure and model development, data assimilation are still, it's still important to keep them in the value chain and support them and resource them. Otherwise, there won't be any application down the line. Just a few recommendations. Reanalysis projects have been mainly developed in the research community with the support of some operational centers, but now there is a growing relevance also for operation and societal relevance. There are still a number of long-standing issues. We talked about the atmosphere, the fluxes, sea ice, deep ocean, and deep cargo. So they are still limiting the full exploitation of all those reanalyses. So there is a clear need for research there. For further coupling and integration, that could tremendously expand the exploitation of reanalysis further. For example, when it comes to energy, water, or carbon budgets. I mean, this is 10 years down the line to really build a comprehensive, coupled Earth system reanalysis, but we should have some kind of long-term vision for the community on that. There are obvious challenges in terms of computing, data storage, and that's valid for the research community, but it's also valid for the operation community. So we need a kind of balanced investment on all those issues to make that happen. Satellite versus computing or in situ observing networks, research and service delivery too. So what's fundamental here is also the respective role and important role of all those communities, academic sectors, operational agencies, and we need to come up with some more we need to formalize that research or operational engagement, and that was a point again made this morning. So this was a short summary of the panel discussion, also maybe a mean to summarize the main aspects of this week. So if there are any specific questions on that, I'm happy to answer them.
It's more more general comment than a question, but to me what's an important point is the complementarity between the different reanalyses. To give example, I know well about the paleoclimate reanalysis, who will never be as accurate as the modern reanalysis, but we can provide a long-term consistency, for instance. We have learned a lot from the modern reanalysis on the method, but now we are making couple reanalysis. We move to Earth system reanalysis, so maybe there are exchange on that, and so the complementarity between the different reanalyses is very strong, as also mentioned by Mathieu for the atmospheric and ocean reanalysis, and I think it's something that should be encouraged.
Absolutely.
So any other points?
Thank you. Yeah, quite right, need for research. But I think we also discussed sort of the future pathway, and we were talking also about roadmaps. That was, as far as I do remember, not an explicit part of the panel discussions, but I think it's important that if we make the statement there's need for research and need for research and need for research, that we also say, maybe start to identify the timeline, that we could say, for example, that in 5 years or 10 years we would accomplish this or that milestone. So I would recommend, if we have this cry out to the funding community to ask for more support for research, that we give them an indication when we could accomplish important milestones. And we can do that. We heard that in that conference. So we can say in 5 years' time or time for the next conference, we have accomplished, better coupling, or we have complemented certain data sets, or have resolved some issues on uncertainty. So I would recommend putting in some.
Yeah, that's a good suggestion. And I think that there are two points to be made here. One is that the outcomes of all these sections and will form the basis of a BAMS-like paper, and that will maybe not have the timeline in it, but at least will carry forward a number of recommendations from this conference. And I think we have, all the basic elements in what we've seen this morning. The second, which is a little bit a more broader comment, is that WCRP, as Diane Blanche highlighted on Monday, is developing its new strategy. And the outcome of this conference will, of course, feed into the new WCRP strategy. An implementation plan, which is also the kind of subsequent document that we will develop.
Just a small addition to Carolyn's point.
Who is talking?
Of creating a timeline, which I think is very important, but it shouldn't just be based on what we can accomplish. It should be what we need to accomplish, because now we are building operational services on top of reanalysis, so we have requirements. And I think it should be presented like that. The research is no longer, research for the sake of research or to serve other research. It's really based on needs of end users of operational services.
Yeah. Absolutely, and thanks again for raising that. I didn't go into the detail when I was referring to the UNFCCC COP, where Jean-Noël is currently. But one important component that will eventually organize, will force us to organize ourselves on that cycle is the global stocktake, because that community, the policymaking community, is expecting climate synthesis or climate indicators, climate assessments on that kind of regular 5-year basis, which should cover, energy cycles, water cycles, carbon cycles, and the like.
Okay, very good. Okay, we give you the floor, the last point.
Sorry, Sean Healy, ECMWF. Just one small technical point. I think you have to be a bit careful when you're writing this about the 7% of observations usage. Yeah, because technically that is correct, but it's not 7% of the information that we use, so you have to be a bit careful there. And also, the point I was trying to make during the panel discussion is I think you have to take a view on the future evolution of the global observing system, be it specifying key observations or something, but we need a reanalysis community view that we can refer to.
Yeah, absolutely. On your first point, I was quoting Roberto, actually. On your second point, I fully agree on that. Yeah.
Okay, very good. Thanks for correcting me. Okay, I think we got to the end of this, so I'll pass the floor to Paul, then back to Mitch, and then I think we are good. So.
It's just a few comments about participation this week. So ICR3 2008, there were 260 participants, 21 countries. 5 years ago, ICR4, 244 participants, so went down. Number of countries, 26, went up. This time, 259 participants throughout the week, 37 countries. So it's clearly really becoming more global. And about the second comment is about digital memories. So we've had the tweets, we've seen that. You also have the videos, they are being posted on YouTube. And then the actual conference material, everything will go online. So all the talks have been already uploaded. If there is any slide you want to see removed, now is the time to do it. After it will go online. I'm not saying it cannot be done anyway, but it will be more complicated. And the posters will also be collected. You'll all receive poster presenters an email next week. And that's all from my part.
No questions for Paul on this? No? Oh.
Just for additional information, because I'm quite engaged in gender balance at my home institution. So I did statistics on the ratio women-men giving talks. And this is 15 women, female talks, and 43 male talks. So we have a quarter of women scientists' participation and 3/4 of male colleagues taking the microphone. So I would like to see that in 5 years' time, balanced. Thank you.
We did our best.
Okay, thank you.
Okay, it has been a very, very busy week. I'm amazed there are still so many people in the room, actually. Yes, so it's time to thank everyone, really everyone. So first, the sponsors. So about a year and a half ago, maybe even 2 years ago, I started having a chat with Jean-Noël, who is the chair of the WCRP Data Council. And we thought, oh, okay, we had the reanalysis conference in 2012 in the US, so it might, and the previous one in Japan. So it might be time to have one in Europe. And as all the Copernicus climate change service business was maturing, coming to life, we thought, oh, okay, that might be a good venture. And actually this week actually demonstrated that this was really a positive idea to bring the research and some climate service element all together, also pulling together the strengths of a top research institution and operation institution like ECMWF in the game. So I think that kind of a triangle of WCRP, C3S, ECMWF really worked perfectly. So thank you very much already to Copernicus, European Commission, and ECMWF for that. There were also other sponsors who made our life really easy. I have to thank particularly the European Space Agency. I don't know if there are any people in the room that I can thank, but surely Joseph Aschbacher and Pierre-Philippe Mathieu really helped us a lot with that regard. Maybe they are still watching online, I don't know. I would like to thank also Anna-Rita. Where is she? Is she still in the room? Anna-Rita Mariotti from the MAP program. She also supported a number of people to attend the conference. EUMETSAT equally. Thank you very much to Alain Ratier, Paul Kounet, Jörg Schulz, Kenneth Holmlund. They are our big supporters and linkages to the climate research. Thank you very much for that. JMA, Shinya, are you still there? Thank you very much also for all your help on and support to the conference. That was really instrumental, including all together with the other sponsors. You all made the live stream possible, and according to the numbers we have, that was a really useful investment. So we'd like also to thank you. I think this conference has been a lively one. We had a good time for discussions, plenty of interventions. So you really made this conference really lively, exciting, and a two-way feedback forum, poster talks, and all the discussions in the various panels, of course. And by the way, hello to all the remote people who are eventually still connected now. Thank you very much also to the Angelicum venue here for hosting us. This has been really an incredible place. And I think that for me, it was the first time that I've been sitting in that kind of very special venue. It's really, it was an amazing idea to pick this venue here. It made the whole meeting quite special. There were also a lot of local support. Catering, who can ever beat the Italian food? That already probably made a case to attract a number of participants here to Rome. And by the way, it also provided a number of opportunity for people to visit Rome during the nightlife, including the early career scientists who discovered some Irish pub downtown somewhere. Technicians, thank you very much to all the audio, video stuff. And all the logistics behind the scene, I won't sign them all because you don't realize, but things happen and suddenly, and you don't even know why or how. So thank you very much for that. You will all be included in that logistics somewhere if your name doesn't appear anywhere else. Many thanks also to the scientific organizing committee, session chairs, panelists, and so forth. We have been all together with the leadership of Paul and Roberto in particular. We have been working for months and months to get us here, so this was really hard work, a lot of conference calls, emails to sort out all the practical details, from program to logistics as well, and make all these useful connections. Thank you very much also to all the early career scientists, and some of them also played the role as a rapporteur. And thank you very much also to Matthias and Andrea. Andrea, are you still around somewhere? Andrea Storto? Oh, yeah. So I would like to invite all the rapporteurs and Andrea and Matthias just to join me on the floor here for a nice picture and a few gifts. So just come over here, and if someone could take a picture, and thank you very much to them. So this small gift is actually a special USB key, and we like to say that young people are key to WCRP. Thank you very much. Andrea and Matthias, by the way, stay here, because I have also another special gift for you guys. Matthias, of course, he's my close colleague, and I need to keep him awake, so this is a cup of coffee, WMO 1. Thank you. Matthias, thank you very much. And Andrea is moving to some new job soon. And I know who's going to be his boss, so he's going to have a tough time. He will have to work very hard, so he will also surely need coffee sometime. Thank you very much to both of you. Okay, three special people. on the local organizing committee. Silke, Eva, Francesca, please join me. We'll take a picture too, I suggest. Yeah, Silke is still working hard somewhere. So we're going to take a picture too, also with the co-chairs. Very good. So now the final question, almost the final question, is whether the ICR5 helped us moving forward. And Roberto, that was your fundamental initial question, right? So have we achieved all the goals? So let's see. Do you have the sound?
Saliamo ancora per il calcio d'angolo, questa volta lo scambio è nostro. C'è Pirlo libero, potrebbe anche calciare. Prova a salire Montani, perde un'altra palla in mezzo, la profondità di Iaquinta cercata sullo scatto di Kufur. Iaquinta va via, è grandissimo Iaquinta, saltato, Vincenzo! Iaquinta, 2-0!
Okay, I think you get a sense that we probably achieved most of the goals of the conference now. So you see the happy organizers. So the picture was taken on Monday morning. So we were still a bit anxious, you know, is this all going to work throughout the week? Taking a picture now, I think we would be a little bit more relaxed than that one. So, all of you have traveled from far away, for some of you. Some are maybe still jet-lagged. So I wish you all a safe trip home. But before closing, I would like to thank immensely Jean-Noël, Paul, and Roberto. Jean-Noël, you know, Noël means Christmas, and we're getting close to Christmas. And for me, this week has been almost a kind of Christmas gift, so to speak. And, you know, Digdi, you are the deputy of Jean-Noël. You've been here all week. You witnessed what happened. You were probably reporting back, Jean-Noël, if we were managing the whole thing correctly or not. But again, I'm tremendously grateful to Jean-Noël for all his help and support to make this happen. Paul Poli. Poli means actually polished in English, or smooth in a way. And I can assure you that his attention to the detail is just tremendous. Thank you very much, Paul. Roberto, you are, you know, our local host, you know. And all the three of you really made a tremendous, tremendous job. So I would like to invite you to stand up for a final exercise, just to thank all these three very, very, very special people. And bear with me. Yeah. I'm not done. I'm not done. Let's pretend that what follows is for the Azzurri. Okay? I hope it's going to work. Yes, it works. Good. So this is especially for Roberto, Paul, and Jean-Noël. And you can join them, actually. We should use the microphones. See you in 5 years from now, somewhere in Asia, probably. So we are already discussing that. Fingers crossed.